have talked about calculating area bounded by a curve in the x-axis so far, right?
Okay. Is there something we can see?
You're good.
Whoa.
Okay. We have talked about calculating area bounded by a curve in the x-axis. So if we're in the xy plane, oops, and we have some function here, and let's say that you were asked to calculate the area bounded by the curve. So on the interval from A to B, some interval, you wanted to calculate the area bounded by the curve and the x-axis. How would we do that? Yeah, we would integrate. We would just integrate from A to B f of x. Yeah?
Yep.
And if we think back to when we were coming up with the definition of the definite integral, like we started with talking about area, right? How did we first approximate area bounded by a curve in the x-axis?
Rectangles.
Rectangles,
the
right?
rule, whatever that you draw the rectangle.
The rectangles. And then we were like, oh, if we use more rectangles, like infinitely many rectangles, that were a width that was infinitely small and had a height of whatever the function value was there, right? We could think about adding up those infinitely many rectangles. So let's say that like that's a rectangle.
Bless you.
We could think about the height of that rectangle as being whatever this function value is minus whatever this function value is. What's the function value down here? 0. Because what's an equation that could represent the x-axis?
Y to 0.
Y equals to 0, exactly. Y equals to 0. Right? Y equals to 0. So another perspective of calculating the area bounded by a curve in the x-axis, a positive function in the x-axis, would be thinking of this as being the integral from A to B of f of x minus 0. Right? Where we're thinking top function is f of x, bottom function is 0, because we're finding the heights of each of those rectangles by taking the top function value and subtracting the bottom function value. And then the dx represents the width of each of those rectangles. Are you guys with me so far? You see where I'm going with this? Okay. Now, if we had a function that dipped below the x-axis, so let's say looked maybe something like this, and we wanted to calculate the area. Area is always positive, right? So let's say you're asked to calculate the area bounded by the curve in the x-axis on the interval from A to B. Again, we would want to be thinking about calculating this area. Now, if we were just talking about the integral from A to B of f in this case, would that represent area?
No. Wait.
It would be what we've referred to as negative area, which isn't like really a thing, but it's something that we can use to visualize, right? Like this, if we're just evaluating the definite integral from A to B here, this would be a negative value. It would be the opposite of whatever this area is. So couldn't we also say that the area would be just the opposite of this integral? Or another way to think about it would be the height of each rectangle, the infinitely many rectangles, like if that sliver represents a rectangle, wouldn't it be top function, the height would be top function minus bottom function? Top function value in this case would be 0, right? Because we're thinking y equals to 0. So another way to think about this would be integrating from a to b, 0 minus the bottom function. Ran out of room. And then it would end up representing the same thing. Sure. So if we are wanting to calculate, we have been technically calculating area bounded between two curves. We just didn't really think of it because one of the curves was always y equals to 0. But we can think about calculating area bounded between two other curves by integrating on the interval from a to b, like whatever the area is that you're trying to calculate area over. So from a to b of top function minus the bottom function. And that top function minus the bottom function gives you the height of each of the infinitely many rectangles. Are we okay with that? Another way to think about it is thinking about applying, so the integral from a to b of f of x minus g of x would be the area bounded between f and g. But another way to think about it is if you were to apply integral properties, right, like splitting that up. So the integral of f of x from a to b would be the area bounded by f in the x-axis. The integral from a to b of g of x would be the area bounded by g in the x-axis. And you'd be subtracting that area that is below g of x. And that would just give you the area bounded between those two curves. Okay, so that also makes sense. So I've given us a picture here. Now this is like a pretty easy one. So I haven't labeled the functions, but 8 minus 2x squared, that's a parabola that opens down. So that means that that would be the blue function here. And then the x squared plus 5 would be the parabola that opens up. And you could reason it out. This is a pretty simple, we're trying to find the area bounded between those two curves. We weren't given an interval, but we're trying to figure out like what interval we would want to integrate over. So we need to think about those 2 points of intersection, right? Because this is the area that we're trying to find. So we need to figure out what this x value would be and what this x value would be. Now just visualizing it, it looks like -1 and 1, right? If you didn't know that, if you weren't given a graph, a picture of the graphs, how could you figure out what their points of intersection are? Set the functions equal to each other. Thank you. So for finding points of intersection, let's just confirm that we get -1 and 1. Now, if it's a calculator active question, have your calculator do it. But if it's not calculator active, you have to think about setting the functions equal to each other. Okay, so then we would get, what is that? Minus 3x squared equals -3. We get x squared equals to 1. So what do you know? We get -1 and we get 1. So that means the area bounded between those curves can be represented as the integral from -1 to 1 of top function, which is f of x, minus bottom function, g of x. And I always triple check that I have the correct, that I've determined like the correct top and the correct bottom function. And then this is something that you guys do know how to integrate. So replacing f and g with their rules. So 8 minus 2x squared minus x squared plus 5. Make sure you have grouping symbols around the entire integrand. You have to have grouping symbols around the f of x minus g of x, any form of it. Okay, so simplifying that a little bit, we will get 3 minus 3x squared for the integrand. And then when we integrate, that's 3x minus x cubed. And then applying the first fundamental theorem of calculus, what is that? 3 minus 1 minus 3 plus 1, which you can leave your answer as is, because if it's a free response, or that simplifies to 4. Questions, you guys? Usually these free responses will come up where this is part of a free response question. Might be calculator active, might not be. They usually give you a graph that shows you the region that you are trying to find the area of, and it's usually part of a question where they will also end up asking you about volume, which is our last lesson. Okay, so this kind of goes 7.1 and 7.2 kind of go together in like the free responses that will occur. They didn't actually have one last year, which was surprising, because like if you go back several years, so I bet there will be one this year that ends up asking about like area bounded between two curves, or maybe it'll ask you the area of a region and like volume. Okay. So I've given us the graphs again here. Just from your knowledge, you guys know that this would be f of x is equal to e to the x. The line would be g of x. And then we want to find the area of the region bounded by those two functions and then the vertical lines. 0. And 1. So we are trying to find this area, which means over what interval will we be integrating? 0 to 1. And then what will our integrand look like? F of x minus g of x, right? Or e to the x minus x. You guys know how to integrate that. So e to the x minus x squared over 2. Right, so that'll be e minus 1/2 minus e to the 0th would be 1. Oh, minus 0. So is that e to the negative 3, or sorry, e minus 3/2? Okay, in your groups that you are sitting in, this is good review for algebra. Sketch the region that you are finding the area for, which is the region enclosed by these two graphs. Both are quadratics. And then find the area. So in your groups that you're sitting with, can you guys please do that? So sketch the regions. And then find their area.
What's up, brother?
That's an approximation at best.
Negative 1, 1, 2, negative 2, negative 3, less, truly plus. 1, 2,
You can figure out what they are.
This graph could be
Two x squared equals 2x.
what is 2x minus x?
Hold on.
I don't know if you
X
can
squared minus
So,
Oh, we didn't read the instructions, did you?
minus 1 is 1.
2x minus x.
x minus 1.
No.
Oh, it says start instruction. You gotta
I got
start.
1 and
start
0.
from there.
Oh, I just got one.
Negative
Right,
1 is
minus
negative 2.
But you used to buy
Minus 1 is negative 3.
You divide it by 2x. X squared equals x. Well, negative 1 squared also equals.
Negative 3.
Wait, no. Hold on.
2
What have
times
you
negative
done?
1.
0. 0 also satisfies the equation.
Okay, so
So wait.
Yeah.
How did? Hold on.
so
I think the graph would be wrong.
4 minus 4 is 0.
I think
Oh,
they're. Okay.
he's
Well,
got
I
the
think
colors
top
too.
one's right.
Yeah, well,
Negative 2 is negative 4.
I think-
Minus 0 is negative 4.
Wow.
I don't think that's.
2 times
You know what? We know this
I
one
see a very
is top,
interesting-
so that's all that matters, right?
Oh, yeah, that's what just do that, it's fine.
Matters
So
in
long
graph.
by
Graph's
far.
fine. Look,
It
it's
takes for
perfect.
57.
Beautiful, right?
That graph, those aren't.
What's up, brother?
Goes from 0 to
Oh,
1.
I see.
What's up, brother? Are you in agreement?
Oh, I see.
Brotherhood or Sindhu?
Um,
I mean, your hood or robbing your hood?
so it's zero, is what we've decided.
It's 0, 1.
Oh, wait, which, I should you put the,
The top, well, this one's the neural. Wait, which one is the, no. It's 2x minus x squared minus.
Where are your parentheses, guys?
So it's really 2x minus 2x squared. 2x, so
that's just two
this
x.
is x squared. Minus
I got
2/3 x cubed.
I got negative 1/3.
So.
Well, it's area, so it shouldn't be negative. So if you get a negative answer, that's a red flag. You need to go back and make sure you had the correct top and bottom function.
Minus 0.
Top and bottom.
Oh!
1/3. Not negative 1/3 because that would be a red flag.
Who would get? Tiny little. Yeah. You got 1/3.
There it is.
Okay, let's look at a calculator active question. Do we all have our, that is recyclable. Thank you.
You're a little bug.
I wonder if your Crocs are recyclable.
You know they're edible, I'm pretty sure.
They're edible?
I mean, they won't tell you to eat them.
A high bar.
I'm not sure about the nutritional calories.
Okay, let's look at this calculator active question. So we have f of x would be this top function. ln of x would be the bottom function because you are familiar with what their graphs would look like. And then we want to find the area of the region enclosed by the graphs of f and g from x equals to 1/2. So it would be this line to 1. Here we go. Okay. So our area would be represented as the integral over what interval? 1/2 to 1 of top function, which is e to the x, minus bottom function. Now this question has to be calculator active for you guys because do you know how to integrate natural log of x?
We do.
Do you?
Integrate, no, we do not.
You don't know how to. You know how to differentiate. You don't know how to integrate natural log of x. So this would have to be a calculator active question. You pop that into your calculator, maybe for practice.
Absolute value.
For calculator practice, pop that into your calculator.
Oh, that's what I had the graphing calculator.
You guys download the app? It's really neat.
Will you have the app on a test bill?
No, but you can use calculator on Teams and use an app in class.
You need to practice with calculator stuff.
Yeah,
It's the same thing.
because you would just factor a -1. So calculator active, you wouldn't have to. Yeah, you could technically. You get approximately, what is it, 1.223?
Yeah, we're all getting there at our own pace.
Well, that's good.
I got verbatim what you got.
Oh. Verbatim. Verbatim.
What is like the verbatim, like equivalent in math?
So it's
You know, like verbatim is like
I agree with Sean. What?
exactly.
1.223.
It's like bars for bars.
Okay. So this one you do need your calculator for. Well, I guess you technically don't, but I'm saying it is calculator active. So you should use your calculator to efficiently solve this problem. So let R be the region bounded by the graphs of y equals to the square root of x and y equals e to the -3x and the vertical line x equals to 1. Okay, so that means the region, and I think it's very helpful if they have not labeled it for you, label it. Region R, capital R, not lowercase r. No need to get creative. Now, here's the thing. For area of this region, we are going to be integrating from whatever this point of intersection is, whatever this x value is, which we don't know yet, like I could call that A, to 1. And our integrand will be root x minus e to the -3x dx. Do you guys remember how to find point of intersection on your calculator? I guess you technically...
We're gonna get 0.239.
Yeah, so what I would do here, you guys, is I would write down what you see. Like this is, you technically could just round to 3 decimal places, but because this is not the final answer, I would write down what you see on your calculator. So like on my calculator, I saw 0.2387341. And I would actually just write that as A equals, so that then I can just leave that as A. I would maybe, you can either type that whole thing out in your calculator in the integral, or you could store it. Do we remember how to store values?
How would you store it from
You would have to type it into your calculator, hit enter, or no, type it into your calculator, hit the stow alpha, pick a letter, enter.
Don't we just need to enter it once anyways?
Well, it depends. It's like if you were having to use it again for another part of a question, it might be worth storing it. This particular question, no, I would probably just type it in.
How would you store it? No, you'd have to type it in.
You type it in. So you would type in whatever A is, and then you would hit the stow alpha, pick a letter, enter.
Okay, so you just have to type it down.
And when you do that, what do we get for the area, you guys?
0.443.
Cool.
Oh, me too, Michael.
That's pretty neat.
Conveniently, value for value.
Bar
This is
for bar.
verbatim, but
2005 AP exam. I was a junior in high school, but I did not take this exam. Calculator active question.
You should give us the exam that you took.
I did not take an AP calculus exam in high school. Okay, so calculator active. So everyone has their calculators out?
Yep.
So let f and g be functions given by, but see how they've so nicely given us a picture and like labeled which function is which. So let f and g be functions given by f of x equals 1/4 plus sine of pi times x, and g of x equals 4 to the negative x. Let R be the shaded region in the first quadrant enclosed by the y-axis in the graphs of f and g, and S be the shaded region in the first quadrant enclosed by the graphs of f and g. So let's find area of R. So let's set up the integral here. What do we need to do in order to set up the integral? We need that point of intersection. Right? We need this x value. So go ahead and type in f and g into your calculator. So go to your y equals, type those in. Make sure you're in radians so you have a rad time. If you're in stats, make sure your stat plot's off.
Oh, yeah, I do.
Find your point of intersection. I got approximately, and just to make sure you guys get this, so 0.178218. So then I would probably make a statement, let A equal to that, or you can just use that value if you want. It might be good to store it because you're going to need it for part B. But then I can say area of R would be equal to the integral from from 0 to A of top function, g of x, minus bottom function, dx. No need to rewrite the integral or the integrand with the rules in it. You can. But technically, this is calculator active. You have reference to those functions. You can now just type everything into your calculator. And because you already typed in the functions into y sub 1 and y sub 2, you can use the vars, right, or alpha trace to pull up the y vars. And you can then insert those into the integral so that you're not having to retype the rule. It'll save you a minute. Right? So if you hit alpha trace, it pulls up the y sub 1, y sub 2, right? You just want to make sure you're pulling out the correct ones into the integral. So you've maybe stored this value for A, and then you pull up the integral, so 0 to whatever A is, and then if this was like y sub 2 minus y sub 1, just so you're not having to retype the rule. You can technically retype the rule. It just maybe saves you some time. But you should have ended up with 0.0648 or 0.065. okay? And then just for this video, I'm gonna set up area of S would be the integral from A to, you find this point of intersection, which is 1.
I'm a brave man. I took AP Chem, alright? I'm not taking it wrong. I'm a brave man. Everyone's in honors.
Look at that, we take on this.
Well, you're built different.
Yeah, Jared's playing. You did. You should suck rap.
Okay, so this is continuing with section 7.1. Now, all of the examples we've looked at so far have been finding area bounded by two curves or bounded by two curves on an interval, where the functions that we've been integrating have been y equals to rule in terms of x, right? And we've been integrating top function minus bottom function on the interval from A to B, where you're reading the x values for that interval from left to right. However, sometimes it can make more sense, or you will be explicitly asked to integrate with respect to y instead of x. So in this case, you can think about turning your xy plane sideways and then integrating from right to left, which would actually, like if you're looking at the xy plane as it normally is, you would be integrating from bottom to top. So thinking about the y-axis, right? So values are increasing as you read up the y-axis. So you would be integrating on an interval that's from bottom to top for it to match the way that we read an interval of y values. Thinking like in a similar way to when we talk about range. We talk about range reading your graph from bottom to top. Okay, so we are going to do an example now where we will find the area of the region bounded by the graphs x equals to 3 minus y squared. So that's the sideways parabola here. So this is, in order to graph on the TI, I had to split up the equations, right? Because our calculator makes us get the y equals. So this is x equals to 3 minus y squared. And then the line here is in the form already of x equals to y plus 1. So instead of it being y equals, we have the x equals. Now, if these were rewritten in the form y equals, that sideways parabola would have two different rules. You could still determine what their area is, but there would be a lot more steps. Like it'll be more efficient for us to integrate in terms of y, to set up our definite integral that represents the area here. In terms of y. So in this case, also whenever we are thinking about turning the graph sideways, like the xy plane sideways, right? Like the top function would actually correspond to the right curve, and then the bottom function would correspond to the left curve. Or we can think about it as, well, now our rectangles that we're using, our infinitely many rectangles that we're using to calculate area are going to be horizontal slices. Where whenever you're trying to now think about it as like the width of the slice that you are determining, or you can still think about it as the length, it would be this function value minus this function value to determine each width. And then this is the region that we are trying to find the area for. Okay, so we need a little bit more information here. We do need to know what this y value would be, as well as what this y value would be, where their points of intersection occur. So we do need to figure out these points of intersection. And in order to do that, and we want the y value now instead of the x value. So to find the points of intersection, both these equations already have x solved for. So in a similar way to what we did before, we can think about setting the rules equal to each other that are in terms of y. So then this ends up being y squared plus y minus 2 equals to 0, which that will factor to be y plus 2, y minus 1. So negative 2 and positive 1. So now whenever we calculate the area of that region, we can set up the integral from negative 2 to 1, and we're thinking right minus left. Okay, so right would be 3 minus y squared, and then minus y plus 1 dy. And we can simplify the integrand here as negative y squared minus y plus 2. And then integrating, that would be negative y cubed over 3 minus y squared over 2 plus 2y. And applying the first fundamental theorem of calculus, that would be negative 1/3 minus 1/2 plus 2, and then minus, what would that be? Negative 8/3 minus 2 minus 4. And you could, as a free response, you could leave answer as is, but that does simplify to be 9/2, 4.5 or 9/2. Okay, so instead of thinking vertical slices that represent all of the infinitely many rectangles, whenever we are setting up an integral and integrating with respect to y, we're thinking about using horizontal slices to represent those rectangles. Okay, a calculator active question. So looking at, we need to, part A, we have to sketch the region enclosed by these two graphs and call the region R. So using kind of our pre-calc knowledge. So I do know y equals e to the x plus 1 will have a horizontal asymptote at y equals to 1. And then that graph has been shifted up 1. So pass through 0, 2. Look kind of like that. And then y equals 2 minus x squared. That's x squared has been vertically reflected and then shifted up 2. So I probably should have. And this is calculator active, so you could always peek at what the graphs look like, but this is going to come down over here. There's going to be a region. Let me fix that. Okay, there's going to be a region that we call R, bounded by those two curves. So that's the region R. A rough sketch of the region R. Okay, so part B, find the points of intersection. You guys know how to do that. Put both of these into your calculator. So y sub 1 and y sub 2. Okay, and then you can go second, trace, find the point of intersection, and remember there are two of them. One of them is easy to see, right? The 0, 2. And then you want to find the point of this other point of intersection here, and you should get, I'm I'm gonna write down what I see on my calculator, negative 0.714556, comma, 1.4894092. Okay, and the question asks us, part C, asks us to set up and evaluate an integral with respect to x that represents the area of region R. So the area of R can be represented, I'm reading from left to right, those x values, so from negative, and you could store this into your calculator, you could define that value on your page to be A or a different letter. I'm just gonna write it down here, 714555620. And then this is an integral in terms of x. So we'll do top function, 2 minus x squared, minus the bottom function. Make sure you have grouping symbols around the integrand. So again, top minus bottom. And then when you put that into your calculator, although it doesn't, oh, it does say set up and evaluate. You put it into your calculator, you should get about 0.082 for that area. And part D is asking us to set up and evaluate an integral with respect to y. So remember, with respect to x, we're thinking about vertical slices, adding up those infinitely many vertical slices, versus when we're talking about with respect to y, we're talking about horizontal slices, and adding those up. Okay, so for us to come up with an integral where we're integrating with respect to y, that means we need to get x equals for each of these equations. So rewriting the y equals e to the x plus 1, we want it to be x equals. So I would first go y minus 1 equals e to the x. And then thinking about rewriting in log form, that would be x is equal to ln of y minus 1. Okay, and then for rewriting the parabola, we will have, what will that be? That'll be y minus 2 equals to negative x squared, or 2 minus y equals x squared. And then we would say x equals to plus or minus the square root of 2 minus y. Well, whenever we do that, the plus the positive square root of 2 minus y would end up corresponding to positive x values, right? So the positive x values here versus the negative would correspond to the negative x values, which would be that side of the parabola, the left side of the parabola. And for coming up with the area here, it looks like we're just going to want to use the left side of the parabola. So the minus here is what will be used. And then we're thinking right minus left whenever we set up our integral. So this is again area of R, region R. And we did find the 2 points of intersection. So reading y values from bottom to top, that means we're integrating 1.48949092 up to 2. And then right function would be ln of y minus 1 minus the left function would be negative square root of 2 minus y. You could also think about it if you were to like rotate the x and y axis, figuring out top and bottom, but I think right minus left works too. And if you put that into your calculator and the integral will still be in terms of x. Sorry, I'm making a video. You can come in, I'm just making a video. We'll get the same answer that we had before, 0.082. Okay, and then our last example is a free response that's calculator active from the 2001 AP exam. So again, you're given a picture, calculator active though, and the regions here, R and S, are labeled. They are in the first quadrant. Region R is bounded by the x-axis, and then the graphs of y equals 2 minus x cubed, and y equals tangent of x. And then region S is bounded by the y-axis and the graphs of y equals 2 minus x cubed and y equals tangent of x. So we want to find the area of R as well as the area of S. Part C, again, we will be covering in section 7.2. So we'll end up circling back to these problems. Okay, so part A, when we want to find the area of region R. Okay, well, in order to find the area of region R, which is bounded by the x-axis, we can actually find this point of intersection and think about splitting region R into two sections. So if we find this x value, for the point of intersection, we can think about integrating from 0 to that x value, and that'll give us the area because it is tangent is positive on that interval. And then we can integrate from whatever that x value is to whatever this x value is for 2 minus x cubed. Okay, so we want to put each of those functions into your calculator. And then to find the point of intersection, so you're again hitting second trace, right? Point of intersection, go through that process. And you should get the x is approximately 0.902155. Okay. And then this x value here, well, you know the y value would be 0, so you could actually set y equal to 0, right? And then solve. So if we subtract 2, divide by -1, so x actually ends up being the cube root, or 2, the cube root of 2, or 2 to the 1/3 power. Okay, so you can represent as an exact value. Okay, so this first region that we are finding the area for would be the integral from 0 to the 0.902155, which again, if you wanted to define that as another letter on here and then reference as another letter, maybe the same letter that you store on your calculator, you could. And then we're going to add the integral from 0.902155 to 2 to the 1/3 power, or cube root of 2, of 2 minus x cubed dx. And while you do know how to integrate both of these functions, it would just be so time consuming. And with the numbers being not exact values, it just makes more sense to put that into your calculator, where you get approximately 0.729. Okay, and part B is asking for area of S. Okay, so for the area of S, We needed that point of intersection for tangent and 2 minus x cubed. So this is the area that we're finding now. And we see top function minus bottom function on that interval. So the integral from 0 to using that same value, so it probably would have been worth it to store into your calculator. And then top function will be 2 minus x cubed, and then minus tangent. Dx, and when you put that into your calculator, you get approximately 1.161 for the area. And again, part C is something that we will be covering in section 7.2.